Let's take a look at section 4.3, which is looking at modeling linear trends. So we're really getting into the equation of that regression line that we started to talk about at the end of the last section and how we can use it to make predictions. So the regression line is a tool for making predictions about future values. It has the form y equals b plus mx, where b is the y value for the y-intercept and m is the slope. So it's just like you would have learned back in algebra. Y equals mx plus b. It's the same thing. It's the equation of a line. StatCrunch in our textbook writes the y-intercept first, so we tend to do that, but it's the same thing you've seen before. We're always going to use technology to figure this out. It can be done by hand, but it's pretty tedious, so we're going to stick to StatCrunch to help us get that equation of the line. So example 4.3, it says, the scatter plot below shows the average number of years in school compared to hourly wages from census data that was taken in 1970. So the number of years in school is the independent variable, and the wages that somebody earns is the dependent variable, wages per hour. So describe the trend of the scatter plot. And so hopefully you would agree that this is a positive trend. So we could say, and it's certainly linear, so we could say a positive linear trend. We could even say this is a fairly strong trend. It looks like the points are pretty close to the line. But in the next part, part B, it says, suppose that you know that R equals 0.883. What does the positive trend tell you about the relationship between the number of years in school and the hourly wage? Well, first of all, I would say that's a pretty strong relationship. 0.883 is a pretty strong number for the correlation value. So if we were to describe this relationship, we could say so you always describe it first in terms of the x value as that goes up. So as the number of years increases, so the number of years of education, the wages, and I'm short on room here, so I'm kind of cutting this, the wages tend to increase as well. So the wages tend to increase as well. The next example, below is a scatter plot that displays the mileage in thousands compared to the price of a used car in thousands. So the more miles we have on the car, we're going this way, what happens to the price of the car, or the value of the car, I guess we can say. So hopefully you'll notice that this has a negative association. How strong is it? It's hard to say. It looks like it would be maybe moderate to me right now, but we don't have the R value just yet. So let's describe it first. It says the scatter plot shows a negative trend. As the mileage of the car increases, so always the X value increasing, its sales price tends to decrease. That's the trend for the most part. Suppose that the equation of the regression line is this. So remember how StatCrunch gives us the equation of the line. This is your y, and this is your x, and this is your y-intercept, and this would be your slope. Use the regression equation to predict the sales price for a car that has 62,000 miles. So I do want to point out one thing. If we go back to the picture for a second, the miles are in thousands. So what I'm going to do here is I'm going to substitute the 62,000 miles in for the x value. Now, there's a slight discrepancy, I think, in this equation because they're giving us the price in 15,000 is the b value. And in our graph, I just want to point out, in the graph, you notice they use the x values in miles in thousands. So in other words, it's not 60,000 or 50,000, it's just 50 or 60. But I think in this case, we need to go ahead and plug in the entire 62,000 in for miles. I don't want you to get too hung up on the units here. I want you to focus on what we're doing. I'm trying to come up with a price estimate for a car with 62,000 miles. So I'm going to replace the independent variable with 62,000, and we're going to do the computation. So get your calculators out with me and make sure you're getting the same numbers I am. 0.034 times 62,000. And so if I put that into my calculator, let's see, I'm getting 15, 6, 7, I'm getting about $13,000, $13,759. And if you go back to our graph, that means that somewhere up in this ballpark here, around 62,000, we would have a car value that's worth a little over 13,000. And does that look right with our data? Yeah, I think to me it does, because there's about 13,000 and some change, and then there would be the 62, so somewhere right about there. All right, so all we did was we replaced the independent variable with the value we asked, and we got an estimated value or predicted value for the price. To find the linear regression using StatCrunch, it's the same thing we talked about in the previous lesson. You're going to put your two columns in and label them. You're going to go to Stat Regression, choose Simple Linear, select the X variable, select the Y value, and click Compute. So, for example, we've got a table that shows the height and weight for 6 different women. Find the regression equation that describes the relationship between the height and weight and answer the questions. And I would recommend that you go into StatCrunch and follow the instructions above. This is one of the few cases where you'll have to type the data in yourself. Normally, remember, if it's a homework question or something like that, it'll populate the data by clicking on that little button in my Stat Lab. But if you go ahead and put this in, I'm getting an equation that looks like this. I've got weight equals, and you can round the numbers however you want to. Usually in the assignments they'll tell you how to round them, but I'm getting negative 442.88 plus 9.0, I'm going to say 03 times the height. And that's the equation that I'm getting from StatCrunch. And then it says use the regression to predict the weight of a woman who is 65 inches tall. So get your calculators out and you're going to plug in 65 for the height and see what it gives you for the weight. So let me write that out. So we have negative 442.88 plus 9.03 times 65 inches. Let's see, 9.03 times 65. And then subtract 442.88. And I'm getting a value of about 144.07 pounds. And that should fit if you look at your graph, so that would be somewhere right in here. We didn't have a person in the sample who was 65 inches tall, but if we did, we would expect them to weigh about 144 pounds. So a couple of things to mention here. Changing the order of the X and Y variables will change the regression equation. If your independent and your dependent variable change, those will change in the that'll change your equation. Now the R value, the correlation coefficient that we talked about in the last lesson, that will not change, but the equation itself will certainly change. I've been using independent and dependent a lot so far in this lesson. So our X value is also called the independent variable, and the Y value, or the Y variable, is also called the dependent variable. There's a couple other terms we may use though. We may also use X variable, we may call it the predictor variable, and then the Y value would be the predicted. One more term you might see that comes up every so often is explanatory. So the X variable we might call the explanatory variable, and then the Y value we might call the response variable. So these are all used interchangeably to represent you the two variables that you're working with. So keep those in mind because you're going to hear them all. Using the same table as the last example, except that the weight is now used as the predictor of the height. So what we've done here is we've swapped the X and the Y. And it says to use StatCrunch to find the equation of the regression line. And so I've gone ahead and done this in StatCrunch, but literally to change this, if you've already got the data in there, you can click on Options and then click on Edit, and it'll give you an opportunity to change the variables. And so my new equation now with these swapped looks like this. The height now is the dependent variable because that's the way I've changed them. Height is equal to 52 point, let's see, 397, so 0.4 plus 0.0, I'm going to say 0.9 times the weight. And I really encourage you to open up a StatCrunch spreadsheet and put these numbers in and actually crunch these numbers with me and make sure you're getting the same equation. I'm not sure it would make sense to estimate the height based on someone's weight, but it might be a situation where you'd want to do that. And so sometimes we do want to switch those variables around and see how the relationships change. let's talk about what we would do with the slope. So interpreting the slope of the regression equation. So the slope of the regression equation tells us how much the y variable changes when the x variable increases by 1 unit. I think a good way to think about that is, if you remember from algebra, your slope you can always remember as your rise over your run. And so in my equation directly above here, my slope is 0.09, but remember I could think of that as 0.09 over 1. You can always put a number over 1 and it doesn't change anything. So what we're saying here is that the slope of 0.09 tells us that the y variable is going to change 0.09 pounds in this case. I'm sorry, 0.09 inches, because that's the y variable, the way I've set it up. 0.09 inches when the weight, in my example, increases by 1 pound. And we'll do some examples of this in just a minute, so you get the hang of it. A regression line with a slope close to 0, the slope close to 0 means there is no linear relationship between the x and y variable. And that'll happen when you have no correlation and your points are just kind of all over the place. Let's go back to this example we had earlier. We were talking about the miles on a car versus the sales price. And thinking about this a little bit more, I actually think this comma should have been a decimal. So I'm going to make this a decimal, and I think that'll fix the issue with the units I was talking about earlier. So let me do that. So 15.867 minus 0.034 miles. The association between a car's mileage and sales price was modeled with the regression line, and here's the equation. Interpret the slope. All right, so remember that this graph, let me go back to it for a second, this graph had a negative association. As the miles increased, the price of the car, or the value of the car, tended to decrease, right? Because it's got a negative association. Okay, so what could we say for this? So we could say, because this is really the slope you can think of as over 1, so we could say for each additional mile on the car. So the over 1, that's your mileage, right? Your y value over your x value. So the 1 is your mileage. So for each additional unit or each additional mile on the car, the value tends to, and it's going to decrease because it's a negative slope, tends to decrease by, and that would be the price, so 0.034 dollars, which I know sounds like a really strange unit, and it is. 0.034, really it's thousands of dollars. I don't want you to get hung up on the unit. That's not the important thing here. I want you to think about what we're saying. The slope you can always put over 1 if that helps you remember it. And so you would say for each additional x value, the y value tends to increase or decrease by whatever that slope amount is. So let's talk about the y-intercept and what does that mean for the regression equation. So the y-intercept, just like it was in algebra, the y-intercept is, is where the line crosses the y-axis. The y-intercept is meaningful only if it makes sense for x to equal 0. And we're going to see some situations where the y value is not meaningful because it doesn't make sense to have an x value of 0. So continuing from the example above, let's see, so we're looking at the same one, the one with the cars. Interpret the y-intercept of the regression equation if appropriate. So what does that mean, if appropriate? Well, does it make sense for x to equal 0 in our car example? Remember, x was the mileage, so that means there are no miles on the car. When would a car have no miles on it? When it is brand new, right? So in this case, the let's see, the y-intercept is the value of the car when it is brand new, or in other words, when it has 0 miles. When it has 0 miles on it. Okay, so it does make sense in this situation because the car can have 0 miles on it when it's brand new. So if we go back to our equation, that 15,000 number, or 15 in thousands, would be 15,867. That would have been the value that the car would have cost when we first purchased it. All right. Take a look at the next example. It was found that there was a strong relationship between heights and weights in a group of 6 women. So this was the equation we had back a couple of examples here. This one that I got from StatCrunch. All right. So the regression equation was given by this. Interpret the y-intercept if appropriate. So if appropriate is really the key thing here. Is it appropriate? What does that mean? That the height would have to equal 0. Does it make sense for somebody to have a height of 0? And the answer is no. It's not appropriate in this case. So not appropriate since the height can't equal 0. You'll also notice too that the y-intercept is negative. We're not going to have a negative weight for somebody, so that's another indication that it's not appropriate. But you really want to think of it in terms of the x value and decide whether or not it's appropriate to have an x value of 0 in that given scenario. Okay, let's look at this example. The scatter plot shown below shows the relationship between population size and the number of fatal car accidents for all 50 states. So use the data to answer the questions that follow. So here's my information from StatCrunch. I've got it plotted. Our population is down here. These are really big numbers because we're talking about populations of a state versus fatal car crashes. So our independent variable is the population. Our dependent is the number of fatal car crashes. And then here is my regression equation right here. So identify the dependent and the independent. All right, so they gave that to us, but let's say it anyway. So the independent variable is the population, and the dependent variable in this case is the number of fatal crashes. Is this a positive or a negative correlation? So what do you think? As we go from left to right, as we read from left to right, the graph tends to go up. So this is a positive correlation. How would we describe it? Well, the strength of this we can talk about because we have the R value from StatCrunch. Notice it's 0.93. That's a pretty high R value. So we would say that this is a strong, because of that R value, positive linear association. Okay. We could say a little bit more, and we can say that as the population, I'm going to abbreviate, population increases, the number of fatal crashes tends to increase. Not always, there could be exceptions to it, but the trend is that it tends to go upward, so it tends to increase. Interpret the slope and the y-intercept, all right? Well, let's start with the slope. So go back up here, your slope is this number, and it's a pretty small number. So what I'm going to do, I'm going to convert that a little bit. I'm going to move the decimal point over till I get a 3-digit number. So I've got let's see, 0.00, let me see, I've got 1, 2, 3, 4 zeros, and then 826. Remember that's over 1, right? That's your slope. And so, whoops, sorry about that, slope. And so I'm going to move this over 1, 2, 3, 4, 5, 6, 7 spaces. So that means I have 826 over, I got to do the same thing on the bottom, move it over 7 spaces. So that gives me 7 zeros. 3, 4, 5, 6, 7. So that means, let's see, 1, 2, 3. Did I miss one? Let's see, 1, 2, 3, 4, 5, 6. I did. I missed one. Okay. Let me erase this a little bit, make this a little cleaner. 1, 2, 3, 4, 5, 6, 7. So listen, don't get too hung up on what I'm doing if this is a little confusing. The units are not the important thing here. What I want you to focus on is how we're describing this behavior. So just to summarize, all I've done is I've taken that decimal to make it a more meaningful number. I've moved it over 7 spaces. So remember, the denominator represents the x value, which is the population. So what could we say? We could say for each additional, now instead of just saying one person in the population, we'll say 10 million, because that's what that number is, 10 million in population. The number of fatal crashes tends to go up because it's positive, goes up. Crashes tends to increase, and how much does it tend to increase? By about 826 crashes. So for every increase in 10 million people in the population, the number of fatal crashes for the state tends to go up by about 826. Now the y-intercept, let's talk about that real quick. The y-intercept is this number. So the number itself is 77, but think about, does it make sense to have a population of 0? Because that's how I would have a y-intercept, is if the independent variable is 0. So the y-intercept in this case, I would say, is not appropriate. Why not? Because we're not going to have a state with a population of 0. Not appropriate because population can't be 0 for a given state. And that's all we need to say about that.